Hello everybody, today we will discuss this what way we can look into the natural coordinate system in case of 3-dimensional problem. We can consider a particular brick element, so it will be easy to understand that how what way we can mapping with the local coordinate system to the global coordinate system in this particular element. So therefore, considering natural coordinate system the xi eta psi, so that it will be centroid of this thing can be OG is the center, and this it is mentioned already that 1, 2, 3, 4. So, I think this is 1, 2, 3, 4 and 5, 6, 7, 8. So, with particular sequence this noded 8 noded one brick element we have considered, and then we define the natural coordinate system as the xi eta psi. So, that is the axis xi eta psi. So, now the of all the information of all the nodes in terms of the global coordinate system, it means that in terms of the x, y, z, that data are available, and that we can get once we look into the discretized geometry, and we have the all information what is a particular node and what is the corresponding coordinate system. Now, once you look into one particular element, we can convert this global to in terms of the local system, so that we can follow the similar kind of the exercise for all the elements, and it will easy to handle, easy to accounting for this particular element, and I think that way we can link between this local and global coordinate system like that. So, zeta equal to x minus x0 by s1, and similarly xi eta psi also in terms of x, y and z, these are the variable, and x0, y0, z0 is the coordinate of the centroid. So, that is way we can make this variant, and S1 and S2 is defined in such a such that twice S1 is represent the length of the edge length. So, here you can see the twice S1, this is along the x axis the edge length, distance between the node 2 and 3. So, that is the twice S1. So, in that respect we can consider this is as S1, S2 and S3 similar way. So, in general the shape function of the element can be expressed in general way n I equal to 1 by 8 1 by xi I eta I psi I like that, and such that this actually if we put xi eta and psi value particular with respect to the that what is the value, if you see that we can map in such a way that with respect to the xi eta psi coordinate it varies it locally it varies between +1 to -1 in that within that range. So, accordingly we can put the coordinate of all these 8 points in terms of that 1 in terms of this particular scaling, that unit is basically 1 1 1 or 1 minus 1 1 depending upon the sign convention or depending with respect to the origin. Now, if we put for example n I say n bit I equal to 1 in this particular case. So, then for I equal to 1 zeta 1 eta 1 and this thing. So, accordingly the sign can be is something like that if I equal to 1. So, if you look into the coordinate of 1, 1 is having 1 minus 1 and -1. So, this is the coordinate of the node point 1. So, we put then xi eta equal to +1 and eta equal to -1 and this equal to -1 such that it becomes, so n1 can be represented like that 1 by 8, we can see that 1 minus 1 plus xi into 1 minus eta into 1 minus psi like that. So, this way we can generalize this thing and such that xi eta psi is the coordinate of the particular point I, and that is I varies equal to 1 to 8. So, this way we can estimate that n1 the shape function in terms of the local coordinate system, but of course, this local coordinate system can be represented in terms of the global coordinate system, it can be in terms of x minus x0 by s1, and similarly for in terms of y and in terms of z. So, that way this term can be defined. Now, once we convert to the global to the local coordinate system, then we can do the formulation, we can see that how the formulation can be done. Now, if we look into the 3-dimensional problem, heat transfer problem also, so then in that case the temperature is the variable. So, each and every node point having some temperature value. Therefore, within particular element this variable temperature nodal temperature in terms of the nodal temperature it can be represented like that T equal to I equal to 1 to 8. So, I equal to 1 to 8 in this cases we have considered the 8 noded brick element. So, then Ni corresponds to the shape function and Ti is the nodal temperature value Ti in that way. Now, This way we can represent we basically interpolate the variable temperature within the element in terms of the nodal values, the shape function as well as the what is the value of the temperature at the node point. Now we know this, we have already shown that what we can discretize the governing equation along in the boundary condition also, but in these cases if we follow the Galerkin weighted residue technique, so in 3-dimensional heat conduction equation, so this part we can see that if we discretize this part of this equation also, so here the heat generation term is not considered. Now see phi is the weighting function and the volume of the solution domain, this this indicates the volume of the solution domain, and then if we do this, put this usual procedure of the discretization of these things and then rewritten in such a way that equation 8. So, equation 8 I think there are, this is the only heat conductivity in terms of this thing, but there is a q dot term and was there also, but then if we look into and even if we tangent heat conduction equation, we have the other term also. So, apart from this thing there is a this term also there and there is a this tangent part also there. So, looking into all the 3 components this thing. Now, if we put this in the weighting function and then we discretize putting in such a way that if we Green's theorem if we apply, so volume integral to convert to the surface integral in that form. So, then this is volume integral is there, this part is there, this part plus this volume integral and this correspond to the surface integral. Now, we replace this surface integral this term also. If we put the appropriate boundary condition, that means in general way the mathematical form of the boundary condition can be written like that. So, this indicates the what is the heat is actually conducted at the surface. Now, once it is heat conduction at the surface and then it is basically n x, n y, n z is a normal vector with this on the surface and is the from the surface, this is the heat loss from the surface by convection, and then q s is the heat flux applied to the domain. So, that is why it is becomes minus q s. So, this is the mathematically with all the boundary interaction we can represent in terms of the what is the heat conduction on the surface, what is the convection on the surface, as well as the if there is any heat interaction by the external flux also, then this can be counted in this in opposite sign, because q s is the input to the surface. In that way the term can be written, and if we look into this boundary condition implement here also, then we can form the this equation that we have already shown or will be showing in the when we exactly discussing the heat conduction equation. There we can show all this in details, that the formulation and then how it is coming, the different elemental part also or contribution from the different components in from the governing equation combining with the boundary condition. So, then if we do all these things, then we can find out discretize this thing, and then we will be getting this particular term in the this thing, that this second term, all this term. If you see, this is because of conduction, the thermal conductivity is involved in this critical, and this we see over the volumetric domain. There also role Cp del T, that means this tangent part also there, and this is the H is there, it is a convective part component is also there, and Qx there. If there is any internal external flux applied to the domain, then it comes into this picture also, and Ht0 is coming. This is the H T minus T0 when we calculate this heat loss by the convection. So, this Ht term is there and this Ht0, that means in reference term is come here also, but that accounts on the surface. And then q dot, if there is any internal heat generation term also, and definitely internal heat generation term has to be accounted over the volume. So, then this is the volumetric term. So, then finally combining this thing, discretize the Galerkin weighted residue technique, and if we look into, if we weighting function can be replaced in the shape function in the form of a shape weighting function is if it is equal to the shape function, then we can reach this particular expression. So, that total derivation can be explained somewhere else, but here point is that what we can utilize the shape function to form one elemental matrix. Now, this once we replace phi as a shape in the form of a shape function, and then we can modify this equation also that way in terms of the shape function, del phi equal to del ni by del x. So, del this is the shape function, weighting function is equal to the shape function. Similarly, del t, t can be represented, t was the variable. So, t can be interpolated something I equal to 1 to 8 in the 8 noded brick element, and that is correspond to the ni and then Ti in terms of the nodal shape function as well as the nodal temperature value. Then we put is the nodal shape function and temperature value, del of this thing, derivative of this is equal with respect to x. Similar way other term can be written in that way, in other way also. Now, this term we can write in the form of a shape function. Now we replace in this thing the weighting function in the shape function, then for I equal to I or j refers to the 8 nodes of this particular element, then we can reach all these components will be coming. Now we can pick up any of the component, how what we can calculate this one contribution from the each component, we can estimate this thing, that we will try to look into this thing. So, if you look into all the components, rearrange all this thing in the matrix form, we can write in this way for a particular element H t S del t by del t, because in this case the with the Galerkin weighted residue technique, but that discretization we are assuming over the space also, not over the time. So, then in that cases we have to time domain we have to consider some shape function, then we can follow some discretization scheme also to get this value. But before discretization in the time domain, on the we look into the what is happening in case of the spatial domain. So, H, T, F, Q all terms are coming in this thing, and in general we can see that H I j is basically in terms of the k, del n I, del n j, del x, del n I n j, del y, n I n j, del z, del z. So, this way we are getting all this term, and this is over the volume. S term comes into this thing, it is also over the volume, rho C p n I n j in this particular way also. Then H other term is the heat transfer coefficient, but this is over the surface, this is over the surface. F q in any heat flux, surface flux is there. If this is the heat loss in account to the reference temperature comes over the surface, and this if there is internal heat generation over the volume. So, these are the typical expression. Some integrand is basically expands over the volume, and some cases it is over the surface. So, this combining all these terms we can form a linear system of the equation. Now, we will see what we can discretize this thing. Now, before doing that discretization thing maybe we can look into this thing, because we have seen that n, see we represented this thing when representing the shape function, n was represented in terms of x. So, therefore, del n by del n x, del n by del x can be written like that, del n by del this thing eta, because xi by del x such that del n by del eta xi and del xi by del x. So, n also in terms of the n can also be represented, we have seen n can be 1 by 8 or that in the particular form xi eta psi also, in that form we can represent. Similarly, plus this del n by del this thing, because n is represented xi in terms of and xi eta psi. So, that is why del n by del eta and del n by del psi also, and accordingly del eta by del x. So, these are the 3 components we can write in this way also. So, that is the represent del n by del n x. Similarly, del n by del y also you can see there are 3 components are there, del n by del z also there are 3 components are there. Now, if we look into the expression del xi by del x, del xi by del x, with respect to that we can find out this expression, that it is become if you remember x minus x 0 by s 1 when I represent the xi. So, then del by del x is something like that 0, such that it become 1 by s 1. So, it becomes constant, this is del xi by del x. Similarly, xi eta del eta by del y also 1 by s 2 and del xi eta psi by del z equal to 1 by s 3. So, s 1, s 2 and s 3 half of the edge length of this particular element. So, then that if you replace these values, then we are getting the expression of the all the expressions. So, n equal to 1 to 8, n 1, 2, 3, 4, 5, 6, 7, 8, then del n by particular x or with respect to y, with respect to z, all this get in terms of the xi eta psi, you can find out all this expression. So, it can to one example also, simply del n 1 by del x. If you see this particular expression, see here it represents 1 by 8 s 1, 1 by 1 minus eta, 1 minus psi. So, like that. So, similarly, you can put any other also, say for example, the last one also, if you look into that del n 8 by del y, it is minus 1 by 8 s 2, 1 by this thing. So, xi and 1 plus psi. So, it means that all this expression we can see that in terms of the s1, s2 the edge length and the this local coordinate system, we can represent this shape function as well. Now, look into this thing, even also the so many all the expression are given also. If you look into in details all these things, we can get the derivative of all this shape function with respect to the local with respect to x, y, z, that means the global coordinate system variable, then we can convert in terms of the local coordinate system. Now, so this domain, once we represent this domain with volume integral over the volume integral this domain, and this domain can be represented the elemental domain in the global coordinate system dx, dy and dz. So, then it is the particular domain, it is the volume integral over this particular domain. So, then it is equal to dx, dy and dz, such that now we know dx equal to S1 in terms of local coordinate xi, S2 eta and S3 psi. So, it means that S1, S2, S3 d xi eta psi, d xi d psi, like that. So, it means that this is the in terms of local coordinate system. Apart from that, we can S1, S2 and S3. So, that means this elemental volume is converted into the in terms of the local coordinate system, local variable, and that way we can convert this thing. Now, once we convert this thing, now if you look into any, pick up any of the particular item, for example, H, for this particular H, I, J, E. So, that particular element how it forms. So, in that cases we replace simply the, it is the volume, it simply replaces that S1, S2, S3 and d xi, d eta and d psi. Replace this thing, this is the things, and S1, S2 and S3 there, and into K, because the K term was there. And then we put this thing in this way, the del n by del n x, that we have already shown that it is actually coming in terms of del n by del x, del n j by del x, plus in terms of del n by del y, del n j by del y, something like that. This way the all these three components are there, and this is the integrand is the in terms of the, because if you see the local coordinate system, it actually varies -1 to +1. So, then we can put the limit -1 to +1. So, this way we can conduct this way. Now, we particular element, say for example, H I J matrix, we can 8 by 8 matrix, it elements can be expressed. For example, H11, how we can be represented like this, H11 equal to K S1, S2, S3 will be there. In this case, I equal to 1 and J also 1. So, del N1 by del x, del N1 by del x, similarly del N1 by del y, del N1 by del y, similarly Z, xi eta psi. Now, here similarly H12 can be represented like this, H133 can be represented like this. So, once we can convert in terms of the basically the local coordinate system, only thing is that it is easy to S1, S2, S3 is the basically edge length that we can look into this. Now, these values of the different shape function can be used, and the value of the H I J can then be calculated from the numerical integration. So, once we look into this numerical this ones -1 to +1, and shape function can be represented N1, N2, basically if you see that N1 this thing, say for example, if you do this further exercise, derivative del N by del Z. So, it is come in terms of the local system, that means local coordinate system. So, once it comes to the local coordinate system, and I can do the numerical integration, and such that assuming the 3 by 3 by 3 integration points, and we can follow the Gauss quadrature rule to find out to calculate the integrand. So, this thing. So, a similar way S can also be calculated like that, rho Cp, the properties S1, S2, S3, and then Ni, Nj, it is there also. So, that can be represented if we replace Ni, Nj in terms of the xi eta psi, then we can perform the numerical integration technique, and there also we can find out that 3 by 3 by the 27 integration points, and we normally do the integration, we can identify what is the this 27 points and what is the weightage of this particular point, and there is that weightage having some fixed value if we follow the Gauss quadrature rule. So, from that point we can estimate the numerical integrated, then we can estimate what is the S I J term can be calculated. So, similar way we can calculate all the elemental term in any kind of this element, it can be S also, it can be H also. So, there this particular element, for example, S I J, so for example S12, here you can see the rho Cp S1, S2, S3, and this thing S12 means in these cases it will be the N1 and 2, put this value, and then we can get this particular expression, that 1 by 64 into 1 plus xi square of that, and 1 minus eta square of that, and 1 minus psi square of that, and this thing. So, now is this term can be done using obtained through the numerical integration using the Gauss quadrature rule, and whether we can use the 3 by 3 by 3 integration point. So, it means that we are not discussing then what we can do the numerical integration, that is in standard numerical techniques book this is available, and this thing standard values are also available. If you follow Gauss quadrature rule, how many points you are considering, and based on that what is the weightage of this particular point, all this data are available in the standard format. We can use this one, and finally we can perform. So, finally doing the numerical integration we will estimate what is the value of S12. Similarly, all the term in the matrix we can estimate the similar way. Here you can see the terms related to the boundary condition also. So, we can see the what we can that look into the boundary condition obtained using the direct analytical expression, that can also be done. We can see that for example, the surface is defined by 1, 2, 3, 4 of an 8 noded isoparametric element, and then on the surface there is a, because when you talking the 3 dimensional analysis, and it is a, if we consider the brick element also, then one face will be on the surface. So, that face we can consider, say it in case of brick element, if we consider, in that case a surface will be having some 4 noded element out of this brick element. So, then in that cases H12 on the surface can be estimated like that also, H12 over the surface, so H12 bar here. So, do not confuse with the previously that H we calculated over the volume, now it is over the surface. So, H12 over the surface. So, same way we can estimate this thing H, S1, S2, N1, N2, this way we can estimate this value. Now, substituting this thing we can just find out the shape function also on the surface. So, N1, suppose there are 1, 2, 3, 4, that is the particular node on the surface. So, then we can estimate the in terms of the local coordinate system xi eta psi, N1, N2, N3, N4, it is a similar way also. For example, this is the point 1, 1, say I am not considering the z component, I am considering only the 1, 1. So, then this indicates the this point N2. So, I think this is point 2, and then plus 1, minus 1. So, plus 1, minus 1, I think this is 0.1. So, this corresponds to the shape function is that 1, 2, I think this is 0.3 and this is 0.4. So, that is why accordingly we can decide the shape function, and then on the surface we can then estimate this similar way also. So, put the value N1, N2 corresponding N1, N2 value, and then we know S1, S2 is the that is already defined, this is total 2 S1 and this is the total is the twice S2. So, half of that S1 and S2 put that is well defined, because that we can get from the global coordinate system. From this what is we can find out what is the edge length for a particular element, because we have the all the coordinate of the particular coordinates of the nodes of all the elements, and that information is always there, and that information is needed actually to calculate for the elemental matrix. So, from there we can find out S1, S2, H is the material property, we define these things, and here we can estimate the N1, N2 and then do the integration, a numerical integration we can perform, then we can estimate what is the value of H12 and for a particular surface. Now, also here we can see the H12 can be estimated analytically, other way also we can put this value S1, S2 minus 1 H1 by, if in terms of the local coordinate system xi eta psi, put all these things, then we can estimate also that it is finally coming to the 4 by 9 H S1, S2. Then finally expressed like that only the surface 1, 2, 3, 4, if there is surface is associated particular 4 node, then HE can be estimated like this, or say in terms of the C H S1, S2 by 9 of H S1, S2 will be the this constant H S1, S2, and then 9, and this we can estimate this way also, and we can find out and directly integrate do the integration, and then we will be able to find out this particular coefficients of this matrix, and that way we can estimate on the surface also. So, this way we can estimate the one particular elemental, all the components of a particular element. Now, once we look at count on this thing, both the what is the, here we are assuming the 1, 2, 3, 4, that is the local numbering of this particular element on this particular surface, but each and every element having some global numbering system also. So, once we do all these things in the local numbering system, it is a follow, say in case of brick element we follow particular sequence and we construct the elemental matrix for node 1, 2, 3, 4 as counting all these nodes also, but that similar numbering, local numbering you can follow 1 to 8 also, but each and node also having some global numbering. So, once you do the elemental formation for all the elements for one elements of a matrix focusing on one particular element, then according to the global numbering we can put the desired position. When we do the assembly, for contribution from by calling from one by one of all the elements. Similarly, the elemental form of a FQ also, you can see FQ means the surface flux. We can see in the, if we look into, there are 8 nodes one particular element, but if there is a contribution only for the surface, then only the surface components are there, this contribution from the surface, remaining we can put simply 0, because that is not associated on the surface, that is the that particular node is the not belongs to this particular surface. So, that is why we can estimate this also, the surface contribution, and similarly for the FH is associated with HT0, S1, S2, 4 in terms of this thing. Here also this is not belongs to the surface. So, in this case we can see there are 8 nodes, contribution 1, 2, 3, 4, maybe it belongs to the surface, but this the other not belong to the surface. So, then once we construct this thing, though if it is not contributing because it is the inside the volume, then we can simply keep that remaining part as a 0. But once with the volumetric heat source term, so then that volumetric heat source term, it is the distributed over the volume. So, then contribution from all the 8 node has to be there. So, that is why you can see, even we calculate the that way the similar strategy also, but here we can see all the there is a contribution, not we are not putting 0, because this is the volumetric part. So, we have the contribution from all the nodes we have to consider. So, that way for in case of the 8 noded brick element, we can simply calculate the required elemental matrix, and once we do for one particular this thing, then we go for assembly, look into the general form. Now, that is okay. So, once we discuss about this the how elemental matrix can be formed one particular a particular problem. So, if it is a thermal problem also, we have shown that if it is a thermal, it is related to the thermal problem. So, we normally solve the heat conduction equation, and from there we look into the what is the governing equation, what is the boundary conditions, and from that point of view we discretize, we follow some kind of weighted residue technique, also Galerkin weighted residue technique. We form the one what we form all the components that comes from the governing equation along with the boundary condition also. Then we construct the matrix for one particular element. Once you construct all the different matrix for a particular element, depending we have to look into that, because not all the elements belongs to the surface also. Which elements belongs to the surface, we have to treat that is the from the because that contribution from the surface has to be there also, but certain elements which inside the volume also. So, that element do not contribute for the surface interaction. So, therefore, in that cases only the contribution from the volumetric term will be there. So, no surface components will be there for this particular element. So, looking into all this aspect, we calculate at one place all one particular element, all the components, the convection term also, the conductivity term, conductivity matrix, convective terms also, and all other, if there is a tangent term also, we can consider all the matrix. So, once it is done for one particular element, one single element, then we call element one, make a loop also, then put the position that contribution from the each node point, accordingly their global position we can put that contribution. Then we make a big matrix depending upon the what is the node number for the whole solution domain. Then for example, the whole solution domain having 100 node point. So, but one element is maybe having only 8 node point. Then we can construct for the 8 node points every all the matrix, then we call this matrix, and then we place it we create the 100 by 100 matrix, because that is the global numbering of the node point. So, then from the there we can put the this contribution from the particular global number of this particular node, and then we assembly for this is, then finally it becomes 100 by 100 matrix. So, then it is in the form of a x equal to b. So, then we solve for this linear system of the equation to get the variable. So, this is the usual procedure of finite element. Now, we see that what is the structure of a finite element model. If we look into the structure of a finite element, it is like that. Typical finite element analysis procedure by a commercial software, normally first is the user defined parameter is required, and that is called the pre-processing. That helps to build a FE model. So, one pre-processing means we have to decide the coordinate system, and we have to decide the unit also, and then we have to give for a particular problem what are the required material properties. If it is thermal problem, it is the mechanical problem also, accordingly you have to define all the properties also. Then we have to create the geometry, that means what is the define the solution domain, and then we have to follow some kind of that discretization scheme also we can follow some meshing scheme also we can define the meshing scheme. For example, we can choose the brick element also for whole the domain, or we can choose some automatic meshing also. Some position we can do some kind of the fine meshing is also required, and some cases maybe coarse meshing is also required. So, all kind of these things, the pre-processing to develop build a FE model. So, before run the actual code, the actual program, so we do all this pre-processing part first, then we do the use the help of a computer do the processing. They conduct the numerical analysis. Processing means it's a simply it calculate the contribution from the each element, then assembly for the contribution for all the elements, then make a global matrix and then solve for the global matrix assuming the linear system of the equation, and then we solve the linear system of the equation. So, once we solve the equation, then we getting the output what is the variable at each and every node point. So, if it is a temperature, it is a thermal problem, we can get the temperature distribution each and every node point. If it is a fluid flow problem, we can get the each and every node point what is the velocity component. So, like that. So, once it is done, then user post processing is also required. So, what way we want to get the result? So, that means do we look into the result that is distributed each and every node point also, or do you want to look into the result in the elemental form also, that means on the one particular element what is the particular value and the average value of the particular variable over the element, or suppose we want to look into the result one within an element also one particular point we want to what is the result. So, once we look into the particular point, then it simply interpolate or extrapolate this thing the surrounding data point node point, and then give the result in this particular point which is not belong to a node point. So, that is how we can see the results also. Or for example, in case of thermal analysis, we want to see the what is the temperature distribution, temperature isotherm also different, we can present the result also. If it is a stress analysis model, we can see the distribution of the distortion distribution, displacement field also we can see that, we can see the strain distribution, we can see the stress distribution, and when we say stress also it is the average value, we can see the equivalent stress value, we can see also, and even individual stress component also we can see the different node points. So, this way the different way we can look into the result, that is called the post processing, just to see the result. It is also user defined. So, user can decide what kind of the results we can see. So, this is the overall structure of a finite element model. Now, in details the pre-processing, here you can, I think we have maybe pointed here that in pre-processing we can get the input data required, then we get the geometry, then basically domain of the solution domain, then what are the material properties, then after that type of the element we can use it, what are the meshing we can do, then how you can apply the load, maybe thermal load or maybe it's a mechanical load, or then finally what you can look into the boundary interaction. So, boundary application of the boundary conditions, all this pre-processing is required. Now, the processing solve the boundary value problem. So, looking into the, or we can see not only boundary value problem, I can say that finite element problem, the whole in the linear system, it finally forms in the form of a linear system equation, and it solved the linear system of the equation to get the output in the each and every node point. Now, results getting in the form of a displacement field, can get in the form of a temperature field, also stress analysis, strain also, and even time temperature history also we can see all sorts of results we can find out at the post processing part. But basic steps of a finite element analysis, just look into this thing, I just try to look into the overall finite element analysis, what we can do this thing. So, following are the steps involved in any kind of the finite element analysis of a particular problem. So, first is the discretization of the domain. So, discretization of domain means in the finite element method, it is a solution domain is there, and say it is divided into small elements, number of sub intervals, it means the line elements called the finite elements. So, it can be the, if it is single dimensional problem, then we can create some kind of the line elements, small segment, and then it is called the finite element. So, basically discretization of the domain is required. Now, collection of the finite elements in a domain is called the finite element in a domain is called the finite element mesh of the domain. So, that is basically that is in term, that is sometimes it is called as a meshing. Meshing means simply discretization of the geometry, total geometry into small elements, and then accounting this when we create small elements, means we have to keep accounting what is the number of elements. We have to, each and every element has to be give a unique number, so that we can identify one particular element. Apart from this thing, each and every node point has to be an unique number, so that globally you can identify this particular node number, and then there is a need of each and every node number, we need the information of the what is the coordinate of this particular node number. So, that is that coordinate is maybe called the global coordinate system in that form. That means data each and every node point, what is the coordinate data. Apart from this thing, it is also necessary to keep on accounting all this thing for each and every element. So, one particular element is associated with the so many node numbers. So, then what is the element number and what are the corresponding node number of this particular element, that information is also required. So, all this data is actually stored once we discretize the geometry in the small elements, and all this data structure is actually required to further processing. Now, derivation of the elemental equations. Once we create the element, then we have to derivation of the finite element equations solving the 3 steps. So, it means that we have to then we focus one particular element in general. One particular element we have to look into the construct the weighted residue technique form of the differential equation along with the boundary interaction if it is over the boundary. Then that is required to do this performing this particular task. So, B assuming the form of approximate solution of a typical finite element. So, in this is a field variable, use the variable in this case is that particular variable, it can be displacement, it can be temperature also, that can be represented like that also, say I equal to 1 to n ui phi I in that particular form. Ui phi I is that this some sort of shape function and then representing some sort of the nodal value of this particular variable. So, this above approximate solution is required to satisfy the boundary conditions of the problem, that is also required also, it should satisfy the boundary condition of the problem, and substitute it into the step 2a to obtain the elemental equation in the form. So, once we do substitute all these things, then we can finally form this elemental equation. So, maybe in stress analysis model we can say the case the stiffness matrix we can form for a particular element and then use the this displacement field, and F is the load vector of this particular element. So, then load in that form equal to A x equal to the B. So, we can solve for x also in these cases to get this variable means which is node point. So, once we form this elemental equation in that particular form and then derive elemental interpolation function phi I and compute the elemental matrix. So, definitely in terms of the if it is phi, so if we put before also that interpolation function or shape function phi I replace the shape function for example, then this thing we construct the elemental matrices. Elemental matrices basically we construct for one particular element, and that particular element it is also necessary the next step also that basically we have to look into that local coordinate system of this particular element, and we have to make the formulation based on the local coordinate system such that same kind of conversation from local coordinate system to can be applied as a master element, and it can be applied for all the elements. And then next step is assembly for the elements. So, identify the inter element continuity condition, identify the equilibrium condition among the secondary variables, and assemble the element equation using the step 3a or step 3b. So, it means that identify the inter element continuity equation. So, that we have to look into this is also necessary that this particular in general we can see that one particular element. So, say this is the element 1, 2, 3, 4, it is associated with some node also and some node common to element. So, we focus on the what is one particular element formulation. So, same kind of can be 2, can be 3, can be 4 also. So, contribution all these things, and then we keep on calling, we make a loop say I equal to say 1, 2, 4 in this case. So, then contribution from element 1 we can put in the global matrix. So, maybe there 1, 2, 3, 4, 5, 6, 7, 8, 9. So, it is a 9 node. So, it can be 9 by 9. So, we can put contribution 1 to maybe 1, 2, 3, 4. So, then we can put 1, 2, 3, 4 according to the contribution in the global matrix. So, if it is done for same thing for next element, second element, same thing we can do for third element, fourth element, accordingly the contribution is put in the global matrix form. Then once it forms accordingly the right hand side also form, then we solve this equation, solve the system of the equation to get the value. So, this is the general steps, basic step of a finite element analysis. Now, before solution, so once we look into the governing equation, all these things, or maybe in displacement problem also even we can look into the boundary interaction, but other way it is also necessary to impose the boundary condition. For example, in strain displacement problem also. In that cases, identify the specified global primary degrees of freedom displacement, and for example, U1, capital U1, capital U2 and capital U3 can be 0. So, that means suppose one is domain, this is the domain analysis discretized, but we need to put some kind of the displacement constant, for example, these 2 points, and suppose displacement constant say U1 and U2 equal to 0 we have to put, and here also suppose U1 U2 equal to 0, U1 equal to 0. It means that once we for the elemental matrix, then we can impose the boundary condition in such a way, then one we form the matrix, the elemental matrix, such that we can impose, we can ensure this particular node point, it may say suppose this is the global number 1 and suppose 1, 2, 3, 4, suppose this is the global number 5, this particular node. So, particular node, once we looking into the contribution, particular node global number is 1, in that cases we have to ensure the displacement equal to 0. Accordingly, we can modify the matrix such the diagonal of this particular matrix in this position diagonal element should be 1 and remaining can be particular corresponds to the row and column. So, it is like this, suppose this is the global matrix also and the position 1 and suppose this is a position 5. So, here also it is a position 5. So, here we can ensure 0 and this particular row and column, here this particular row and column we can ensure the remaining are 0, and the right hand side if it is displacement 0 means this 0 and fifth position it is 0 and remaining can be some other value, such that we have to modify this matrix in such a to impose the boundary conditions on this particular node point, and such that when you solve this one it will ensure that exactly we will be getting the displacement equal will be 0 for this particular node point, and both the components U1 and U2 would be 0. Accordingly, we can so that we can modify this matrix. So, this is the way to impose the boundary condition, normally displacement boundary condition associated with any kind of the stress analysis problem. Now, once we do this imposition of boundary condition, ensure then solution of the assembled equation. Then we go for the solution of the assembled equation, and that is the there are so many solution strategies are also there, and then looking into we will discuss also that different types of the solution strategy, but finally we can solve this particular equation. Then once it is done, then post processing of the result. So, once solution is done, then we are getting the displacement field each and every node point. If there is a two dimensional problem or 3 dimensional problem, accordingly we can get the displacement field along, say if it is 3 dimensional problem, we can get the what is the value of U1, U2 and U3 on each and every node point. If it is 2 dimensional problem, we can get only the 2 components U1 and U2. So, like that. So, then computation of the primary secondary variables at the node point of interest and graphical representation of the result. It is also possible graphical representation of we can extract the data point, and from the data point we can graphically we can represent the result. But although we are getting the results in terms of the U1 U2 in that displacement field, but we know that displacement can be converted to the strain field, and from the strain also we can estimate the stress field. So, this way we can convert displacement to the strain to the displacement field. So, strain to the stress field. So, that it means that we are getting, even if you know the stress field also, from here we can estimate the equivalent stress field also, that means single value of the stress components or the individual component of the stress. Similarly, individual component of the strain, all kind of information we will be able to get in the during the post processing of the result. So, in that different way we will be able to get the results from the analysis. So, that is the post processing of this. Okay. So, that is the basic steps for any kind of the finite element analysis. Now, the solver is one of the important part associated with any kind of the finite element based problem, and in this particular problem most of the time consuming part is the to get the solution of the linear system of the equation. So, definitely if you look into details about this any kind of the finite element based problem. So, to solve this particular system of the equation, it takes the maximum time this thing, or other way you can say the computational time entirely depends on the choice of the solver in any kind of finite element based problem. So, basically a finite element solver in general can be 2 types, one is the direct solver and another the iterative solver. So, direct solver means it is a kind of how it works. So, first preprocessor, this assemble all this thing is done. So, once the after assembling the global stiffness matrix is ready, then we go for solver. So, then we try to look into the how we can solve this matrix. So, then there is a need of the solver. Then once solver will get the output, then we look into the post processing of the result, the different way we can represent the result. So, this is the usual procedure, this thing, but solver is the main part in the finite element processing, I think, in terms of time, in terms of the computational cost or other computational cost in terms of time. So, then solver can be direct solver or it can be iterative solver. So, direct solver means solution is converged by the inversion of the K matrix, that is simply inversion of the K matrix we can get. This direct solver is possible, but iterative solver means in this cases the solution is converged with multiple iteration is required with the error is being minimized. So, that means we can assume some initial value of the solution, then we can follow some strategy or some algorithm, we get the next value and then compare with the previous value. So, that is why some iterative way we can calculate the result also. So, definitely if it seems that if you look into in that way, the direct solvers what you can get the exact solution inversion of the K matrix, and maybe so many iteration is involved in the iterative solver, but looking into these two aspects, it seems that direct solver can be more suitable in case of finite element based problem. But in actual practice, if the element size or maybe number of nodes is huge in a particular domain of analysis, for example, say in usual problem it is 50,000 or 1 lakh of node points are available. In that cases, if you look into any kind of the direct solver also, it takes a huge time consuming effect. But maybe nowadays some iterative solver has been developed so that very quick, although we can getting the approximate solution, but approximate results also using the iterative solution, then the time maybe it can take the less time than that of the direct solver. So, let us look into this thing, but what is the difference between direct solver and the iterative solver. So, direct solver actually it is based on the Gauss elimination or the lower triangle or upper triangle decomposition. So, we know the Gauss elimination method if we put this thing, but in this case initial no initial guess is required to start the solution process. So, maybe as compared to the iterative solution method, then we can get an exact solution at the end of the computational time. That is very important, because if you look into the direct solver, you can expect the exact solution at the end of the computational process. It is simply following the Gauss elimination method. Also, if you follow this method, basically it is simply inversion of a particular matrix, then you can expect the exact solution of this particular. But maybe if handling of the solution process becomes very difficult with the increasing number of the node point unknown variables. So, basically in terms of the node points we understand in the finite element method. So, more number of node points means more computational time. So, that if it is increasing is too much of node point, then it is very difficult to get a solution, or maybe other we can say that computational time is used. It consumes more memory, the solution procedure, and it can be computationally expensive if the number of unknowns are more. That is already explained this thing, but general steps to reach a solution is that actually the general step system of the linear equation. So, system of the linear equation in the form of a matrix we can for, and then we basically have to inverse this matrix to get the solution. So, it can augmented matrix can be formed, and it can be from the forward elimination. If you look at the Gauss elimination, forward elimination, Gauss elimination processes, there are two steps. One is the forward elimination and second one is the back substitution. Forward elimination means it basically form in the particular matrix is converted to in terms of the upper or lower triangular matrix in this particular form. So, when it is converted to the upper or lower triangular matrix, then from the back side maybe I can say that if symmetric matrix you can form in this way also. So, that triangle. So, once it is done, forward elimination is done. So, this basically convert this particular way this matrix, then back substitution it start the solution from this thing, because here is the remainings are 0 and here we can get the solution, direct solution, this is the first variable. Then once you get the solution, use this solution value for the next step. So, then 2 and next 3 step 3, like that from the back we can get the solution of one variables. So, variables 1, 2, 3, 4, 5, 6 for example. So, we get the solution for the from back substitution means we start with the solution from the get the solution of x6, the variable 6. When get the variable 6 solution, then in the matrix we can use the value 6 value, then we can get the solution of 5. When for the 4 also we need the solution of 5 and 6, then we can get the solution of the 4. Like that back substitution. So, then finally, we are getting the solution, we can solve this particular equation. So, I am not going into details how the Gauss elimination works also, it is available in the any standard book and standard module, this particular procedure is available. Now, iterative solver, of course, they start with the initial guess of the solution, but minimizes the error with each iteration to converge the particular solution. So, basically it works the minimization of the error in the with the each iteration to converge in the particular solution. So, that is there. But stopping criteria or tolerance has to be specified to the solver to stop the iterating. Thus, it is trade off between the computational time and accuracy. It is very important because it is a trade off computational time and accuracy, depending upon that what kind of the stopping criteria you can decide, or maybe tolerance we can give. So, accordingly we can assume particular solution which is more close to this satisfying the tolerance criteria or stop criteria, then we can accept this is the solution. So, definitely we cannot expect the exact solution of the equation using the iterative technique. So, since we are putting some stopping criteria tolerance value, so definitely in these cases we can expect the approximate solution of the particular equation. So, that is in that aspect it is different from the Gauss elimination method, because Gauss elimination method you will be getting the exact solution of the particular equation. Now, iterative solvers are more suitable for the computationally expensive problem as they are easier to parallelize. So, basically parallel computational method is easy to form if we follow some kind of the iterative calculation. So, that is in that sense it is very important. So, in that way it is advantageous. So, you can easily do the parallel programming when you handling the iterative solver or iterative solution method. So, in that cases, so there is a huge number of elements are there, huge number of nodes are there. So, large number of system of equation, then in that cases the iterative solver may be it will be advantageous if it is possible to solve this parallel solver has to be developed. So, therefore, since the iterative method starts with the initial guess value, so it needs the use of conjugate gradient method to determine the direction. Definitely once you start the initial value, then what may be the increment of the particular value, one particular direction, what can be the that. So, that is why conjugate gradient method can be used to determine the direction in the initial guess solution you will remove. And apart from that, the iterative solvers, the convergence of the iterative solver also depends the very good initial guess. So, initial guess is very good also, then we can expect the quick converge solution of a particular iterative solver. So, that is also very important. So, there are several algorithms also there such that we can quickly have a very good initial guess for the iterative solver. So, in the iterative solver can be suffer from the oscillatory behavior, some that also possible. So, instead of the converging the solution, there may be start to the diverge. In that cases, there may be iterative solver may not be the effective in this particular situation. So, that is why that we can say the limitation or maybe some kind of the disadvantage of this iterative solver also there. Okay, so now once it done this thing, the last part of this module 2 also, then apart from this elemental form, all this finite element process also, then maybe what we can do the what are the basic steps of the finite element method and how we can do the elemental form, elemental matrix, and apart from that what are the basic steps and what kind of the solver we can use in the solution. So, that is the basic thing that was associated with the basic thing of a finite element method. But apart from that, sometimes there is a need to look into, specifically I am talking about the welding problem also. So, in that cases there is a need to track the interface. So, it means that it is easy to understand that if your domain is very fixed also and fixed domain, and we can do the analysis over the fixed domain also, we can get the solution on this particular domain also, assuming this thing. But if there is a interface evolves the interface, for example, in the welding with respect to time, the weld will grow. So, weld will grow, and that is that whirlpool domain, and at the same time the free surface also may not be exactly the flat what was the initial state. So, during this after the welding process, the initial you can get some curvature also, or sometimes if there is a material deposition on the particular domain also, then this domain which the free surface profile of this particular domain may not be exactly what was the initial case. So, in that cases it is necessary to look into the what is happening the interface, or other way also mathematically how we can track this interface. So, to track the interface also there are the several strategy, several algorithm also there. Overall that means the basic frame of the finite element method, or we can say that the other has been developed, that is the extended finite element method. So, this is the extended finite element method is in particular if there is a discontinuity or some kind of the free surface, there is a need to track in any kind of the problem, then there is a need to further extension of the finite element method can be used, which is called the extended finite element method. We will look into that. But apart from that, there are several other interface tracking method which can be integrated over the basic finite element based analysis to simply track the interface in a finite element based problem. So, let us look into this thing in general, the interface, but when you looking into the what do you understand by interface, there is a two different way to track the interface. One is the interface capturing and another is the interface tracking method. So, interface tracking and interface capturing techniques basically widely used in the computation of the flow problems, if you see the flow problems. So, with the moving boundaries is there and presence of the interface. So, in that cases we can use the interface capturing and interface tracking method also, and this particular problem, say fluid particle interaction, fluid object and the fluid structure interaction, free surfaces and the two fluid flow, two phase flow also, and flows with the moving mechanical components and flow with the moving, all these particular cases which is very challenging, actually computationally challenging. In that particular cases we can find out there is a need to look into the situation of the interface. Now, in from the point of view, mathematical point of view, or we can say that analysis of the finite element method, in that case the interface tracking technique requires the meshes that track the interfaces. So, to track the interfaces, we either conform to the mesh and update it as the flow evolves, track the position of the mesh nodes in a Lagrangian fashion, and then imposition of the boundary condition will be easy in that cases because node lie on the fender. So, in that cases we have to in the Lagrangian fashion, then maybe in that cases the interface tracking means the interface is moving along with the mesh also, such that every time it is a mapping with the particular net, and there is a need to look into the remeshing of this particular element if it is a large deformation problem also. So, in that cases the interface lie with the node point. So, that is the call in general, that is called the interface tracking method. But interface capturing method is the two fluid flow or maybe computation are based on the fixed domain. In this case the capturing method is equal to the domain is fixed, but externally it is possible to capture the interface. So, without not conforming the every time the mesh along with the interface, the movement of the interface. So, in that cases domain is fixed, over the domain interface can evolve. So, but interface can be tracked externally. So, that is called the interface capturing method. So, it means that where the interface function making the location of the interface is compared to the capture the interface. So, based on in this case Euler and description, and that define the interface implicitly on a fixed mesh. So, basically it is necessary to define the implicitly the interface over the fixed domain, and then we can track the interface looking into the different strategy. So, there are several interface tracking methods, the particle tracking, volume of fluid methods, level set method, phase field method, these are the very common method. So, interface tracking method we normally use. I have discussed this particular different type of methods one particular module, most probably it is the fluid flow module. So, maybe you can look into that particular module, the what are the different methods we will be getting in details, but here we just try to look into the what is the extended finite element, how it is different from the classical finite element method. So, extended finite element method is a basically numerical technique based on the generalized finite element method. So, that is called the GEFM, or it is and the partition of unity method, PUM, sometimes it is called the partition of unity method. So, in this case the powerful for discontinuous problem. So, it is mostly associated with discontinuous problem in mechanics, such as the crack growth, complex fluid and the interface and so on. All this kind of method we can use the extended finite element method. So, it is basically independent of the internal geometry, physical interfaces also, because we remember it is a fixed domain, we are implicitly tracking the interface. So, in that cases we can use the extended finite element method, such that meshing and remeshing difficulties in discontinuous problem are not there. Basically remeshing is not required in discontinuous problem. So, discontinuous, for example, there is a crack. So, what we can how crack propagate and what we can track the mathematically in a particular problem. So, in that cases this crack creates some sort of discontinuity in the domain also. So, then the usual procedure is to capture the discontinuous discontinuity. So, simply remeshing in this particular domain. So, that is the one way to capture, look into the crack, what the evolves of crack in a particular mechanics problem also. But other way also, if you want to avoid the remeshing, again creating the meshing in this particular domain, we can follow, no, there is not necessary to remesh this particular domain, rather we keeping the same mesh, but with different way we can track the discontinuity. So, that is why there is a need of extended finite element to understand this thing. So, this discontinuous field is entirely independent of the mesh, that is very true, that it is independent of the mesh, and enriched elements with the additional degrees of freedom at the crack surface or crack tips may be required. So, some sort of enriched elements has to develop. We have to understand what is the enriched elements. Not only simulate the cracks, but also heterogeneous materials with the voids, and if there is inclusion, all kind of this interface with tracking or in discontinuity can be captured using the extended finite element based method. Now, we know the shape function can be used to write the expression for the displacement field in terms of this thing, shape function and the displacement field u is the Ni and Ui. So, where n is the ith shape function and u as the nodal value. So, this is the u variable and parameter u and the ith node, and p represents the number of nodes in this particular element that we note, and we have already seen, even it is temperature or displacement field, whatever, we can represent this within particular domain within element is in terms of the mapping with the shape function as well as the nodal shape function as well as the nodal values. Now, the even same way coordinate can also be interpolated with respect to the nodal value. So, suppose x is the variable, this can be coordinated in terms of the shape function and coordinate of the particular node point. So, Ni is the shape function and xi represents the coordinate of this particular node, and p is the number of nodes of this particular element. So, this way it can be interpolated. Similar way, any kind of the variable, it can be temperature, it can be displacement, all can be in way it can be interpolated with this variable. Now, partition of unity, we started with these things. Basically, they define a set of the m functions fk within a domain such that k equal to 1 to m within a particular domain. We define the functional fk, f as a function of x is equal to 1. Now, it can be easily shown that by selection of the any arbitrary function, say xi x, xi ta, psi x, the following property is automatically satisfied: k equal to 1 to m, this is the functional form, and this is the thing such that it equal to psi x. Xi x. So, based on this thing we can find out the set of isoparametric finite element shape function Nj also satisfied the condition of partition of unity. So, that thing such that j equal to 1 to n Nj x is basically 1, that we have already seen the summation of this shape function of this thing is also satisfy the partition of unity, but n is the number of nodes in each finite element. So, n equal to number of nodes in each finite element. So, that also satisfies this partition of unity method. Now, theoretically, the increase of the order of completeness that has been achieved basically in this particular case, and computationally targeting the higher accuracy of the approximation by including the information obtained from the analytical solution, we can say that u can be represented like this. So, in these cases the information from analytical solution also helpful, such that theoretically we can increase the order of completeness, then we can achieve this thing particular relation n u equal to j equal to 1 to n n j u j, that is why. So, in terms of the m basis function p, then we can write this way also, there is m basis function, then pk ak in this way also we can write. So, where unknown ak determine the form of the approximation at the nodal point. So, basically ak determine the form of approximation, what are the different form of the approximation in the nodal points can be represented. Two ways of enriching this approximation: one is the instinct enrichment, that enriching the basic vector, other way the extinct enrichment, that is enriching the approximation. Two different way the approximation can be done. So, enrichment is done at the node point where the continuities exist. So, enrichment done one particular node point, there is existence of the discontinuity. So, in that way the approximation space enhanced by including the new basis function into the standard approximation space to capture the discontinuity. So, in that way enrichment function are added to the standard approximation such that the basis function, linear basis function, for example standard first order linear basis function is this one, 1 x and y. Now, new enrichment terms can be like that in terms of the f1 and f2, two different functional forms, such that p consists of the linear basis function and as well as the enrichment. So, it consists of basically we define this thing to capture the discontinuity. We can use some sort of enrichment function also. Now, this uses the extrinsic basics to increase the order of completeness. It means that to order of completeness, that from the theoretical part we can see that. Then apart from this conventional thing, this thing we can use the other, we can use the PK, that means functional form, simply to order of completeness we can enhance, such that AK is the additional degrees of freedom associated with the enriched solution. So, we can enrich the solution, but that enrichment can be done locally on the selective elements also, and then additional degrees of freedom is associated with this particular enriched solution. So, in general, partition of unity enrichment, partition of unity enrichment is written something like that, consists of this, the ux is the u is the variable, this part which is we have seen in the classical finite element method. Apart from this thing, we can use this other functional form. So, here f p u are the set of partition of unity function. So, based on this theory, that extended finite element has been developed. So, we can see that in XFEM, first the usual finite element mesh is produced. So, usual finite element mesh is produced, then by considering the location of the discontinuity, a few degrees of freedom are added to the classical finite element model in selected nodes only near to the crack or discontinuity to provide a higher level of accuracy. So, then enrichment normally happens near I think few degrees of freedom is basically added in the selected nodes near about the discontinuity or near about the crack. So, that way we can develop the extended finite element method. So, the enrichment function added to the standard finite element approximation in the XFEM, extended finite element method, it actually serve the important purposes. So, they encode the location of the interface into the function space itself, which allows for the application of both the Dirichlet and Neumann interface conditions without the need for a conforming mesh. It means that there is not necessary to conforming mesh on the exactly on that. Once we look into the enrichment functions are added, that may not necessary to follow the conforming mesh, such that XFEM can be approximation to calculate, for example, the velocity field at the point of x located within the domain. So, in this cases use the velocity field, you can use that 1 to n is the ui is the nodal values, particular node point, n is the shape function, and plus this extra term. So, in this ni is the standard finite element shape function of the particular node I, and but mj is the local enrichment function, ui are the nodal variable, and aj are the all additional unknowns and all additional unknowns aj, because and m is defined by the number of enriched nodes. So, that means this term comes because of the enriched nodes and extra degrees of freedom particularly associated with the enriched node. Now, point is that what I can decide the enriched node. So, that we will see later on, but elements with only some enriched nodes are called blending elements. So, elements which having enriched nodes, that is called the blending elements, and this partly enriched elements needed the special treatment to avoid any computational error, that is also required. The local enrichment function can be expressed like that also in terms of the shape function, and this xi is the global enrichment function in terms of this thing, global enrichment function we can write the local enrichment function. So, that is why global enrichment function can be the weak discontinuities enrichment function defined normally in terms of the sign distance phi. So, then that is the in that cases also global enrichment function can be in the weak discontinuities, that enrichment function defined normally in terms of the sign distance function phi. Now, however, it is necessary to solve the level set equation, transport equation to update the evaluation of the interface. So, it also required, because to update the evaluation of the interface, it is necessary to some sort of the level set transport equation to solve. So, that transport equation can be represented like that. So, phi equal to, here phi is the that sign distance function. So, using the sign distance function we can identify the interface, and this governed by the conservation equation. This is the level set theory. In terms of the sign distance function we can see the phi x the level set field, and in terms with phi x the level set field may be in terms of the sign distance function, and v is the velocity vector that advex the level of the set field. So, v is the advex the level of the set field. Then how is the one particular interface we capturing using these things, that is represented by sign distance phi functional form. Then what way it moves that with the velocity v also, velocity gradient, that we can put this. So, therefore, this equation is necessary to solve to define the interface also. So, therefore, phi x t is the sign distance function in this particular case, which stores the shortest distance through the interface, and this label set field is discretized by using the standard finite element method basis function. Standard finite element basis function, we can discretize the domain, this particular equation, then we can solve for this thing, this particular field, and then that field define the actual interface in terms of the shortest distance to the interface. It stores the data in such a way. Now, we can able to understand these things, example XFEM also. Say suppose this is the crack length. So, what we can crack length, but what we can do the enrichment of this particular. So, then we can identify that from through which element it passes, then particular element from this we can identify that element and then associated node also, and such that this associated node and element can be enriched, this thing particular. So, it means it is a locally enriched with some locally identified nodes element through which the discontinuity exists. Even some inclusion also, if suppose this is the inclusion on hole in the particular shape. So, we can identify what is the enriched element, and then we can identify what is the enriched node also, and then on that particular enriched node or element we can apply the extra degrees of freedom what we have seen also, that there is a one particular terms comes because of this, because of the enrichment. So, once we do the enrichment of this particular node point, then we can develop this thing, and the total matrix stiffness matrix, we can solve for it and we can get the interface. Even to get the interface also, it is also necessary, or to track the interface also, it is also necessary to solve this particular equation also in a finite element domain the same way, such that we can able to track what is the interface. And there are the few issues in these things, that polynomial integrands we can use the normal Gauss quadrature method also in classical finite element method, and you can get the results also, but ordinary Gauss rule do not accurately calculate the integration of enriched function. So, once you use the integration of the enriched function, then ordinary Gauss rule may not be give the accurate result in these cases. So, in that cases what happens, it is necessary to subdivide the enriched element. So, suppose this is the enriched element, in this case suppose this is the enriched element. So, pick up this particular enriched elements. So, then in this particular element subdivide the enriched element such that it will increase the integration point. So, you can is a small integration point. So, small domain such that we can increase the integration, the subdivision is required, so that integration points can be used. Then using the Gauss quadrature method or maybe numerical integration techniques if we follow, then we can expect the very good result. So, that is the two things. One is the identification of the enriched elements or enriched nodes also in this particular, and then applying the enrichment function, all this locally, all this particular domain, apart from the what we are following in general way, the classical finite element methods. Apart from this is the extra thing to track the interface also, solve this equation, plus we need to solve this particular equation that govern that interface motion equation. We need to solve interface motion equation to track the interface also, that is also required, and that interface motion equation we can use the we can define some label set function, maybe we can use a sign distance function to get the to track the interface also. At the same time how it is moves we are able to capture using this. So, this is the in general way the overall the extended finite element works, but if you want to go more details about the extended finite elements, you can follow any kind of the standard book to work into this particular direction. So, this is all about the module 2, the fundamentals of the finite maybe of finite element methods also. But in this particular module I have tried to discuss the basic this thing, but only the finite element method itself is a one subject, one course also. So, here I just overview the particular part or emphasize on this particular element, which may be some sort of working knowledge to develop some kind of the finite element model specifically applicable in case of the welding process. So, thank you very much for your kind attention.